Yeah, perfect.
All right, and so now we have Thomas Martin from Unidata, who's going to continue our investigation into AI/ML foundational concepts.
Okay, thank you so much. Yeah, and what a great talk to lead into this one. We're definitely going to cover some similar stuff. So this talk's going to be on AI/ML foundations, or ML is for everyone. So I'm gonna try to hope to demystify some of the things. I'm going to do a presentation sin of there's code in my presentation, but it's only like 10 lines total, so it shouldn't be that bad. So AI and ML is not needed nor appropriate for every scientific question. You know, there's a lot of domain expertise in this room. Like we've seen, you know, a lot of these National Weather Service models are quite good. There's also some things where machine learning can be a big lift. It can really help. And so, you know, it's definitely, you know, you need to incorporate domain expertise, machine learning scientists, experimenting, trying it out, but I'm definitely not going to be up here saying machine learning is going to improve every scientific research question that you have. So in the room, just you can raise your hand. Who's currently working on machine learning in week-to-week work? I know there's a couple. Groovy. Who would like to use machine learning in future projects? You think it's interesting and neat and you want to do more of it? Oh. Any concerns with machine learning or AI techniques? And if you have, I will actually take hands and answers. If you have a short 1 or 2 liner, like what is your biggest, go for it.
People think that using AI is the science as opposed to a tool to do the science.
Yeah, it is a tool in the toolkit, and I think that there is a part of science to kind of sharpen those tools or make those tools better, but it's definitely, you know, we need to think about the scientific process as well. Any other sort of things that, you know, makes you pause before like you're gonna jump in with 2 feet doing machine learning work?
How fast that world is expanding.
Yeah, no, even for people who, you know, are researchers at NCAR, you know, it is going super quick. So comparison of data science versus scientist versus whatever you want to call yourself. You can find all these graphs or all these blogs on Medium. I would say if you work with data, you're a data scientist, and you know there's elements to truth of all of these graphs. One thing I do just want to point out is this hacking skills, which we might self-identify our programming skills as and expertise. The overlap is danger zone, and I think that is a good thing to sort of point out. So what is machine learning? This is generally for supervised learning, but at a very high level. I would say, you know, previously we have a data set and a program. It could be linear models you define or some sort of if, then, or else sort of statements, and you get an output. Machine learning is a different paradigm where you put in data and output and you get a program. Okay, now this is a bit of a thought experiment. Let's say you have a set of data points. There's purposely no axes, no labels on this. That's all part of the fun. You know, with these 5 data points, you might draw a trend like this. You know, again, we don't need super deep learning to put in this trend. You know, you might disagree with the slope. If you add more data points, it might change. But let's say your collection of data points looks more like this. Would you want to connect the dots in a squiggly line? You know, this is going to hit every data point we have absolutely perfectly. We're going to, you know, do very well on all our scoring metrics. Or, you know, you can do something a bit more basic. But if you add in new data points to be more generalizable, which sort of model is going to be a better fit? So in the last talk, we talked a bit about overfitting. With these machine learning models, you want to be generalizable to new unseen data. You don't want to overfit on your training data that you have seen. Now, while this PowerPoint has, you know, a dozen or so data points, imagine if you have hundreds of thousands to millions of data points. Again, we can't draw these relationships by hand. You can't QC these relationships by hand, and that's truly where the power is for machine learning, is figuring out these relationships and patterns sort of at scale. So again, it's a bit hard to see on the screen here, but I'm a huge Scikit Learn fan. It is a machine learning package in Python. They have kind of an interesting cheat sheet. I would say you don't need to follow this exactly, but it is kind of a good roadmap to start. If you are truly lost with your data set and don't really know where to go, this is a great place to sort of start out on. But I will say, while machine learning is great and you can do a lot of things, knowing your data exploration, data viz, stats, all of those tools are still very, very important. We don't get to replace all the things we learned for the past 50 years and replace it with machine learning. Machine learning builds on all of those skills. Just to get in more supervised data model choice, if you have point data, observations, or station data, you might want to use gradient boosted decision trees or Scikit-Learn type models. If you have gridded larger data sets, that's where deep learning might be a better fit. But that's not to say with gridded larger data sets, you can't use gradient boosted decision trees or Scikit-Learn type models. Okay, so one sin of presenting, I'm going to go through code. So we have 5 lines of Python up on the screen, and we are going to do a regression model all together. So the first line, so from Scikit-Learn, we're going to import SVM, so that is the support vector machine module. We're going to define our X and our Y. Our Y is what we're trying to predict, but this is our training data. One thing to look at from the X, it is multidimensional. You can have as many input vectors as you really want. You're going to define from the SVM module, we're going to use the support vector regression. We're going to fit, so we're going to do dot fit with X and Y, so this data set that you defined up here. Then with that model, we are going to predict using a new X. Again, this is a toy data set. We could draw this line in Excel, but you can imagine something that's 100,000 or 500,000 data points, where you probably wouldn't want to define it this way, but if you're good with, if you know pandas and intermediate Python, to get started with Scikit-Learn is not an insurmountable hill. Now, there's a lot of steps I cut out. This is sort of the minimum viable product for Scikit-Learn, but again, I just wanted to, it is for everyone. If you want to do unsupervised learning or a basic k-means clustering, again, from scikit-learn.cluster, you import k-means, import numpy, you define your X. There is no Y since you're looking for the labels. And then you can set up your model. So here I'm defining 2 clusters, the random state, and then I'm going to fit to that X. Then k-means show labels would then label each one of these data points with a cluster of either 0 or 1, since there's 2 clusters. You can change the number of clusters to 3, 4, 5, put it in a loop, do a whole string of clusters all at once. Again, this is just a minimum viable product to show how little lines of code you need to do machine learning. Now, deep learning. Many deep learning models can be written under 100 or 300 lines of code. There's many open source examples out there. I have some on my GitHub I'd love to point you to. Many researchers focus on one framework, either a TensorFlow person or a PyTorch person, but actually ChatGPT is pretty good at translating from one to the next. And so while deep learning is more lines of code, it's not thousands of lines of code. It is still, I would say, relatively straightforward. I think TensorFlow might have a little bit easier on-ramp than PyTorch, but really, do you like Coke or Pepsi? A lot of the time, they get to the same place. So the future, as much as I hate, a lot of AI talks have like a lot of blue backgrounds and brains with computer chips and robots and all that stuff. I don't deal with robots in my day-to-day work, but this image was generated with DALL-E 2, which is a large language model. I know some faculty in the room is probably having some heartburn around ChatGPT and all the rest of that, so we are going to get to that now. So generative AI, things are changing exceptionally fast. ChatGPT, GitHub Copilot, DALL-E and Google Bard, those are amazing, amazing tools. But we are so far away from having a weather GPT or subsurface GPT or GeoGPT. So you can ask it for a radar image, and that radar image, you won't know what day, what sensor, it will look like a radar image from a distance, but it won't really give you any of the information or the metadata that we all crave. I find these tools to be super useful as a developer tool, but unsure how it will impact science in the future. I think it's changing very fast. I'm not saying we will never use large language models for scientific discovery, but definitely today it's not quite there yet. There's so many legal and privacy questions and probably some cheating questions for faculty. So before you go all in on large language models, I would be careful, read some pros and cons, and make your own decisions. And if you're at a big company, you chat with legal. But even with that, even with ChatGPT, I would say that there's no better time to learn machine learning techniques. Like we just went over today, we did both supervised and unsupervised machine learning in Python in 10 lines of code. So that barrier to entry is decreasing all the time. Even for deep learning with a GPU, you can use Google Colab, or our Science Gateway has those GPU capabilities. Even though ChatGPT can write a ton of code, it can't interpret what's happening, it can't bring meaning to it, it's hard to score, and those are really what we all bring to the table. And in the future, many practitioners or students or future employees will be using machine learning outputs. So understanding how these are built and assessed, I think will be a more important skill than building these sort of machine learning systems. So yeah, just a little bit more on the workforce side. You might see these AI-enhanced weather startups, Jupiter Intelligence, Climate AI, Tomorrow IO, a lot of remote sensing, Earth observation. Whether you believe in AI or not, definitely VC money in the workforce thinks there's something there. So we'll see how a lot of these shake out next couple of years. But if you think about where things are going, it's definitely using some of these machine learning tools. Now, I don't want to, me personally, I don't want to get into the business of predicting the weather 52 weeks out. I think, yeah, there's a lot of issues potentially with some of that marketing. But again, it is sort of an interesting time. Again, we just had a job, in the last talk around some of these skills. So future and current sort of workforce skills. So if some of you are faculty in the room, I would say the future is cloud. A lot of these data sets that we're working with can't fit in memory or on your laptop anymore. And so the old download, analyze, push out, that won't die, but if you're using 100 gigabyte data sets, that is getting exceptionally difficult with the things we have on the tables in front of us. Jobs will definitely change. IT services will modernize. I think of some of our Unidata staff, how their careers have changed over the past 10 years. Figuring out how to get CUDA drivers to work, ChatGPT hasn't solved that problem. And so we still need development engineers, machine learning engineers. I think that, yeah, jobs are definitely going to change. Even with ChatGPT that can spit out tons of lines of code of Python, I've even ran into this, and I would say it's an open discussion. If it doesn't work from ChatGPT, is it faster to write it from scratch, or to me to debug the output when it doesn't work. And I think for some days it takes the same amount of time. It's just a different effort. But again, knowing object-oriented Python or the scientific Python stack is still going to be a great skill. I think we're very far away of no-code everything. As far as job availability, this is a very rough. I just put it into Indeed last night for the state of Colorado. There's 50 times the amount of Python jobs as Fortran jobs. Now, if you look at those Fortran jobs, they are definitely probably more related to the atmosphere climate realm. There's a lot of instrument engineers, National Weather Service, defense contractors dealing with weather and satellites and things like that. But if we think about future language growth, I would just sort of keep this in mind. That being said, it's very hard to kill languages. I think there will still be Fortran devs in 5 to 10 years, but I think they will become increasingly specialized sort of in that space. If you're looking for more resources, I know the talk right before me had a lot of great resources that I've also used in my day-to-day. There's 2 blogs on the Unidata blog with some books and some courses. One I will highlight here is the ECMWF. They have a new MOOC out around machine learning and weather and climate, which I think would be appropriate for a lot of the people here. And that's an interesting course because it goes over theory and it has code. And then with that, I know that was super quick, but if you have any questions or thoughts, let me know. Thanks so much.